Hello, good evening everyone. I hope all are doing well. Anyway, we all welcome all of you to the Infinity Learn JEE YouTube channel. This is me Surya, your chemistry faculty for this particular session. Hi Anish. Hi, good evening. Tejas, good evening. Okay, today in this lecture we are going to the very most important part of the chemical bonding and molecular structure, that is the hybridization part. So far we have discussed all the important topics, right? Starting from the causal-Lewis approach, then VBT, then VSEPR. Then now we are moving to the major part, that is the hybridization. Let's quickly start it. Okay, what do you mean by the hybridization? That is the main topic of this today's lecture. Before that, I hope all of you guys are revised through the last topic, that is about the valence bond theory. Whenever we are discussing about the postulates or the limitations of the valence bond theory, I have already discussed that the theory fails to explain the geometrical shape, right? The VBT failed to explain the geometrical shape of some of the molecules like water, methane, etc. That drawback or limitation was later modified by the Linus Pauling by the concept of hybridization, right? Hi Sonu. So hybridization is the part of valence bond theory which is modified by the Linus Pauling by the concept of intermixing of orbitals, right? By the concept of intermixing of orbitals having nearly the same energy to form the new type of orbitals. Clear? The intermixing of some of the orbitals having equivalent energy and the equivalent shape will form new type of orbitals. That formation is known as the hybridization. The resulting orbitals are known as the hybrid orbitals. Clear? So first of all, we have to discuss about the features of the hybridization. There are 4 important points are given, which is given from our NCERT textbook. The first one is that the number of hybrid orbitals, right? The number of hybrid orbitals that is equal to the number of atomic orbitals which is formed in the hybridization, forming in the hybridization, right? In the case of hybridization, the atomic orbitals are involving or intermixing each other. So we can say that the number of hybrid orbitals which is formed as a result of hybridization should be equal to the number of atomic orbitals which is involved in the hybridization. The second point is that the hybridized orbitals always have equivalent energy and shape, right? Yes. Now the third one is that the hybrid orbitals, they are effective in forming stable bonds, right? They are effective in forming stable bonds than the pure atomic orbitals. The last one, in the case of hybrid orbitals, the hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between the electron pairs, right? So that they will become the stable arrangement. So geometry is also predicted by the type of hybridization. Clear? These are the main features of the hybridization part. Yes, fine. Now let us go to the conditions that satisfy the hybridization. What are the major conditions that satisfy the hybridization? Again, 4 more points are there. You just have an idea about this. The first one is that the orbitals which is present in the valence shell of the atom is undergoing hybridization, right? Always valence electrons or the orbitals which is present in the valence shell are undergoing the hybridization. The second one, the orbitals undergoing hybridization should have the almost equal energy, right? which is the main feature of hybridization also. The third one is that the promotion of electron is not a necessary condition for the hybridization. Promotion of electron means excitation. You will get an idea about while I am discussing about the examples. Excitation. The promotion of electron is not a necessary condition for the hybridization. Next, the last point. It is not necessary that only half-filled orbitals participate in hybridization. Whenever we are discussing about the orbital overlapping, we have studied that only half-filled orbitals will undergo overlapping, right? But in the case of hybridization, it is not necessary that only half-filled orbitals will participate in the hybridization. Even in some of the cases that completely filled or the filled orbitals or the valence shells also take place in the hybridization. Clear? Is the points are clear? Yes, fine. This is the major part of the chemical bonding chapter as well as the hybridization. We have to study these 5 types of hybridization along with their examples in detail. So as you can see here, the first one is the sp hybridization, sp2 hybridization, sp3, sp3d and sp3d2 hybridization in detail. I need your complete attention throughout the session because it is little bit complicated, but when you get the idea, it will be very easy. Ready? Now let us start with the sp hybridization. The name itself suggests that there will be only one s and one p orbital, right? One s and one p orbital, which means that sp hybridization happens by the intermixing of one s orbital and one p orbital, right? Intermixing of one s and one p orbital to form two sp hybrid orbitals, right? Which means that the number of atomic orbitals involved in the hybridization should be equal to the number of hybrid orbitals formed. So, 1s plus 1p form 2 sp hybrid orbital. Clear? This is one of the s orbital or any of the p orbital you can take. So it will undergo the hybridization to form this type of structure in which two sp orbitals are, right? So two sp orbitals, it should be in the equal shape as well as in equivalent energy. sp hybrid orbital. These are the two sp hybrid orbitals arranged in the sp hybridization having a bond angle of 180 degree. Then the shape will be known as the linear shape. Clear? This is a structure of a two sp hybrid orbitals. Clear? Now we have to calculate the percentage S character in this sp hybridized orbital. How we can calculate that? So total two sp hybrid orbitals are forming in which only one s is present, right? So I am taking 1 by 2 into 100, which means 50%, right? 50% S character is present in the case of sp hybridization. Then what about p character? Again 1 by 2 into 100, or you can take the difference between 100 and 50. It is again get 50%. So we can say that in the case of sp hybridization there will be 50% S character as well as 50% p character. Clear? Now let us explain the sp hybridization with an example, that is BeCl2 molecule. Whenever you are getting any of the molecule, first you have to find out the hybridization of the particular molecule by using the steric number concept, right? Steric number concept. Okay, this will be the steric number concept. The number of sigma bonds plus lone pair electrons, that should be a number. According to their number, you can predict the hybridization of molecules, right? So, if I am taking here BeCl2 molecule, the first thing you have to be done that BeCl2, right? In the case of BeCl2, beryllium having the least electronegativity, it will be the central metal atom, right? Central atom. So, in the case of beryllium, what will be the valence electrons in beryllium? Valence electron in beryllium. Two, right? Yes. So, how many atoms are surrounding the beryllium in the case of BeCl2 molecule? That is the number of surrounding atoms. 2 chlorine, right? So, I am taking here 2 chlorine atom, which means that it is understood that 2 sigma bonds are formed between the beryllium atom. BeCl2 molecule, 2 sigma bonds are forming. So, I can say that this will be the number of sigma bonds, right? It is equal to 2. So, which means that the beryllium has a valence electron of 2 in which 2 bonds are forming, which means lone pair present on the BeCl2 molecule or the beryllium is 0, right? 0. So, now I am taking the steric number here. What will be the steric number here? 2 plus 0, that is equal to 2. Whenever the number becomes 2, which means that it will be the sp hybridization, right? This will be the sp hybridization. Is the thing clear? How we can calculate the steric number and predict the hybridization? Pooja, which point I want to repeat? Steric number calculation, right? A number of sigma bonds. As you already know, beryllium has the valence electron of 2, in which 2 chlorine atom is presenting, which means that 2 sigma bonds are forming there, right? So, in which 2 valence electron, 2 are undergoing the bond pairs, which means that there is no any lone pairs, right? Whenever we are calculating about the steric number concept, the number of surrounding atoms should be the number of sigma bonds. That will be the little concept. So here it is 2 chlorine atoms. So I can say that 2 sigma bonds are forming here, in which valence electrons having 2 is forming 2 bond with that, which means lone pair is 0 there. So while calculating the steric number, you will get the number of 2. 2 stands for the sp hybridization. Clear? Now we have to draw the hybridization of BeCl2 molecule. For that, I am just writing the electronic configuration. I am drawing the configuration here. 1s2, 2s2. In the ground state, it is showing like this. Now, there will be the promotion of electron, right? There will be the excitation of electrons. So I can say that here, while exciting, one of the electron will go to this p orbital so that it will undergo sp hybridization, right? So now I am writing the excited state configuration of Be. One s 2 is already here. One of the electron from 2s orbital is going to the 2p orbital, right? Then one of the 2s orbital and 2p orbital undergo sp hybridization here. It will undergo sp hybridization, or it will form the sp hybridized orbital. Now, what is the surrounding atom here? Chlorine, right? So whenever we are calculating the electronic configuration of chlorine, it will be this is, right, neon after 3s2 3p5, which means that 3p set having one unpaired electron is present there, right? So the one of the unpaired electron from the chlorine will bind with the sp orbital. So I am writing here, this red one represents the electron come from the chlorine atom. Clear? First they are forming the sp hybridization. This will be the, now here it will form in the sp hybridized orbital. After forming the sp hybridized orbital, the one of the atom which is present in the 3p set of the chlorine atom will combine with this sp orbital to form, or overlapping with the sp orbital to form, completing the electronic configuration, right? So in the case of structure or the molecule, it will form like that. Okay, this will be the general structure of sp hybrid orbital, right? This should be in the equal shape. Okay, this is the sp orbital. Then what will happen here is already one of the electron is here, then another one is here. Now overlapping happens, right? 3p orbital of the chlorine. These are the 3p orbital of chlorine. Clear? So, whether it is an axial overlapping or sidewise overlapping. Our previous class we had discussed about the sigma and pi bond, right? This is the axial overlapping or sidewise overlapping. Axial, right? Which means that this is our sp hybridized orbital. This sp hybridized orbital and 3p orbital of the chlorine will undergo axial overlapping to form spp or psp sigma bond, right? psp sigma bond. Here one of the sigma bond and here next sigma bond. That is representing the structure of BeCl2. This BeCl sigma bond corresponds to this overlapping, and this BeCl sigma bond corresponds to this overlapping. Is that clear? Okay, fine. This is the structure of BeCl2 molecule according to the sp hybridization. You can say that bond angle is 180 degree and the structure is, or the shape or geometry is linear, right? Clear? Now let me move to the second type of hybridization, that is sp2 hybridization. What do you mean by sp2 hybridization? How many hybrid orbitals are forming there, or which of the orbitals are participating in the hybridization in the case of sp2 hybridization? That will be the definition of that hybridization. sp2, right? 1 sn 2 p orbital. So you can see here the intermixing of 1 sn 2 p orbital. In total, 3 equivalent sp2 hybridized orbitals are forming in the case of sp2 hybridization. Okay, this will be the arrangement of 3 sp2 hybridized orbital having bond angle of 120 degree and its geometry or shape is given as trigonal planar. Then what about the S character, percentage S character? Total 3 equivalent sp2 orbitals are forming, right? In which 1 is sp, so I am taking here 1 by 3 into 100. How much it is? 33.33, right? 33.33%. Then the rest will be the percentage p character, that is equal to, either you can take it as 2 by 3 into 100 or take the difference between 100 and 33.33. It will be 66.66%. Clear? Yes, Pooja, you are correct. 33.33%. And the percentage P character is 66.66%. Clear? Now let us explain the sp2 hybridization with the example. Here the example is given as BF3. What is the first step you have to do whenever you are getting any of the molecule? What is the first step you have to do? Steric number calculation, right? Steric number calculation. This is a central atom here in the case of BF3 molecule. Boron, right? BF3 molecule, boron has the least electronegativity, so it will form the central atom here. So we can say that first we have to calculate the valence electron in the presence of boron atom. Boron is having the atomic number of 5, right? So we can write it as 2, 3, which means that 3 is the number of valence electrons there. So I am taking here 3 valence electrons. Then how many surrounding atoms are present here, or the number of sigma bonds? How many surrounding atoms or the number of sigma bonds present in the BF3 molecule? Pooja? 3, right? Yes, Anish, you are correct. Number of sigma bonds means the 3 fluorine atoms are surrounding here. So we can say that again the number of sigma bonds is equal to 3. So we are taking the difference. We will get that again here lone pair is also 0. Lone pair is equal to 0. That is 3 minus 3, that is equal to 0. So in total, while adding 3 plus 0, you will get the steric number is equal to 3, right? If it is getting the steric number of 3, which will be its hybridization? 3. sp2, right? Clear how to calculating the steric number or predicting the hybridization of BF3 molecule? The next step, we have to draw the structure or draw the hybridization of the BF3 molecule. First, you have to write the ground state electronic configuration of boron. One is to 2s2 2p1, right? 1s2 2s2 2p1. So in order to get the sp hybridization, we will write the excited state electronic configuration, which means that here one of the electron from the 2s orbital will go to the 2p orbital, right? 2p orbital. So the excited state electronic configuration of boron will be again 1s2 right? One of the electron from the 2s orbital is going to the 2p orbital, so it will form sp2 hybridized orbital, right? sp2 hybridized orbital. Now you have to find out the valence shell in the case of fluorine, right? I am writing here in the case of fluorine. Fluorine means 9, right? So 1s2, 2s2, 2p5, right? 5, 2, yes, 2p5. 2p5 means 2p set having unpaired electron, right? Which means that one of the electron from the 2p set of the fluorine atom will overlap with the 3 sp2 hybridized orbital, right? Clear? Okay, these red electrons are representing the electrons comes from the chlorine atom. Here it is fluorine, so it is in the 2p set of fluorine atom. Clear? Now we have to draw the structure. This will be the sp2 hybridized orbital structure, right? So that here the 2p of the chlorine is, 2p of the fluorine is getting overlapping here. Clear? These are the sp2 hybridized orbital. P is forming. So we can say that this is sp2p sigma bond, right? sp2p sigma bond. Here is also sp2p sigma bond. In total, 3 sp2p sigma bonds are forming here, right? In the case of BF3 molecule. Clear? So in total, what will be the structure of the BF3 molecule? We can draw here. This will be the central atom boron. Then fluorine is like this. These 3 sigma bonds correspond to each sp2p sigma bond. Clear? Then bond angle will be 120 degree and the the geometry is trigonal planar. Can we move to the next type of hybridization? That is sp3 hybridization. Okay, the next one is the sp3 hybridization. As the name it suggests that 1sn 3p orbitals, right? 1sn 3p orbitals undergo hybridization to form 4 equivalent sp3 hybridized orbital. So we can draw the structure here. This is the one of the sp3 orbital. Then the next one, and again next one, like this. It should be in the equal shape, right? My drawing is not perfect. Okay, like this. Okay, this will be the arrangement of 4 sp3 hybridized orbital having the bond angle of 109.5 degree and its shape should be tetrahedral. Then what about the percentage S character? Percentage S character. Total 4 orbital is forming, right? In which 1 by 4 is the S character, then 1 by 4 into 100 it is 25%. Then the rest of it is percentage P character, that is equal to 75%. Clear? Now here is the example, that is a methane molecule. First, again you have to calculate the steric number here. Steric number should be equal to the number of sigma bonds plus lone pair, right? Here the number of sigma bonds is the 4 hydrogen atom is surrounding, so it will be the 4. Number of sigma bonds will be 4. Then valency of the carbon is 4, in which 4 are satisfied with the 4 hydrogen atom, right? Which means that lone pair is 0 here. So steric number is equal to 4. 4 means it will be sp3 hybridization, right? It will be the sp3 hybridization. Now in order to draw the hybridization of CH4 molecule, first you have to write the ground state electronic configuration of carbon, right? Ground state electronic configuration of carbon. GS stands for ground state. So I am taking here 1s2, 2s2, right? Two P2, right? 1s2, 2s2, 2p2 will be the ground state electronic configuration of carbon. Then, now we have to do the excitation here. There will be the promotion of electron happens, which means that one of the electron from the 2s will go to the 2p side orbital, right? 2p side orbital. So it will form so in total 1s plus 3p, it will undergo sp3 hybridization, right? sp3 hybridization, or it will form the sp3 hybridized orbital. Are you getting my point? Okay. Here the surrounding atom is hydrogen, right? Hydrogen in the case of only 1s1 electron, right? So 4 hydrogen atom will undergo overlapping with the 4 sp3 hybridized orbitals. So I am representing the electron from the hydrogen by blue color. So this will be the electrons comes from the 4 hydrogen atom. So we can say that this is from the one hydrogen, this is from another hydrogen. First it will form the sp3 hybridized orbital. After that 1s orbital of the hydrogen is overlapping with the sp3 hybridized orbital to form the sp3s sigma bond. JEE hybridization means the intermixing of the same shape or having the equivalent energy orbitals to form new type of orbitals are known as the hybridization. The number of hybridized orbitals forming with the number of same number of atomic orbitals undergoing hybridization. Simply we can say that hybridization is the process in which many of the orbitals can intermixing, right? Having the same energy. Clear? Now we can draw the hybridization structure here. Okay, this will be the one sp3 hybridized orbital in which 4 hydrogen atoms are overlapping, right? 1s orbital of 4 hydrogen atoms are overlapping. I will be representing this overlapping with the yellow color. So what is happening here? First it is forming the sp3 hybridization, then it will represent the sp3s sigma bond, right? It is again the axial overlapping, so it will form sp3s sigma bond. Again, in total 4 sp3s sigma bond is forming here. That is why we are getting the structure of CH4 like this. Right? CH4 having the bond angle of 109.5 degree and its geometry is tetrahedral. Clear? Hi Saloni. Okay, this will be the structure here. I think it is clear for everyone. Now, another example of the sp3 hybridization, that is the NH3 molecule. As you already know, while calculating the steric number, you will get the value of 4, which means it is undergoing sp3 hybridization. As it is undergoing sp3 hybridization. In the case of ammonia molecule, first you have to write the ground state electronic configuration, right? Ground state electronic configuration of nitrogen. 1s2, 2s2, 2p3, right? Here the point you had to be noted that this is the third postulate or third feature of the hybridization, right? There is no any necessary for the promotion of electron or the excitation, right? Here in this case there will be any chance of excitation, which means that in the case of 2s orbital there will be 2 electrons, and in the case of 2p orbital there will be 3 unpaired electrons, right? Then it will undergo sp3 hybridization. sp3 hybridization. Then what will happen? 3 hydrogen molecules are present there, right? While forming the 4 sp3 hybridized orbital, we can say that, but I will write here. The 3 hydrogen, the 1s orbital of 3 hydrogens will overlap with the 3 of the sp3 hybridized orbital to form sp3s sigma bond, right? sp3s sigma bond, 3 sp3s sigma bond. Then what will happen to these these paired electrons? Any idea whether it will undergo hybridization or not? It will not undergo hybridization, it will remain as the lone pair. It will remain as the lone pair. So while drawing the structure of NH3, you can identify that. Okay, this will be the structure of NH3 molecule. These 3 sigma bonds correspond to the sp3s sigma bond. Then the unhybridized orbital, this sp3 orbital, right? This will represent the sp3 lone pair. Clear? Okay. Then finally, this will be the structure of NH3 molecule. The point is that there will be the lone pair, right? According to our valence bond theory, we have studied about there will be the repulsion, right? Sorry, VSEPR theory, there will be the repulsion. So we can say that lone pair bond pair repulsion is more. Lone pair bond pair repulsion is more than bond pair repulsion, right? So we can say that the general bond angle for the tetrahedral structure or the sp3 hybridized structure is 109.5 degree, but here it will change into 107 degree in order to minimize the repulsion, right? 107 degree. And we can say that the shape, because of this lone pair, the shape is changing here, or geometry is changing here, and its shape is represented by the bond pairs, right? If you are ignoring this lone pair, you will get this, these hydrogen molecules will form the pyramidal shape, right? So we can say that shape is pyramidal here. Clear? Okay, this will be the structure of NH3 molecule along with their lone pair. The second case, it is the water molecule. Again, while calculating the steric number, you will get the steric number is equal to 3, that is equal to steric number is equal to 4, that is equal to sp3 hybridization. Then write the ground state electronic configuration of oxygen, you will get 1s2 2p4, right? It is 2p4. Then what will happen here? Only 2 hydrogen atoms are coming, right? So this will form the hybridization here. Total it will form 4 sp3 hybridized orbital. 4 sp3 hybridized orbital. Then 2 hydrogen atom. 1s orbital of the 2 hydrogen atom will overlap with 2 of the sp3 hybridized orbital, right? Which is having the unpaired electron. So I can write it as here. This blue color represents the electrons coming from the 2 hydrogen. Electrons from the hydrogen. What will happen here? sp3s overlapping is happening, which means it is the sigma bond formation, right? So we can say that this will be the sp3s sigma bond formation. These pairs, right? These 2 electrons from the 2s and 2p. Okay, these 2 electrons from the 2s and 2p remains the lone pairs. That is why we are seeing the 2 lone pairs in the case of water molecule. Are you getting? Okay, now we can draw the structure here on the hybridization. These are the 2 lone pairs. Then here it is forming the overlapping, right? From the 1s of hydrogen atom. 1s of hydrogen atom. It will form 2 electrons, right? So this will represent the sp3s sigma bond, right? sp3s sigma bond. Then it contains 2 sp3 sigma bond. Then these 2 are the lone pairs, right? These are the 2 lone pairs which is present in the case of water molecule. Again, in order to minimize the repulsion between these electron pairs, the structure will be like this and bond angle is around 104.5 degree. Yes, you can see here. This will be the structure. In order to minimize the repulsion, this will be arranging like this, having the bond angle of 104 degree 3 minute. It is 3 minute. 104 degree 3 minute. Having the shape of, whenever we are ignoring the lone pairs, it will have the shape of bend shape, right? Shape will be bend. Clear? So far we have discussed about the sp hybridization, right? Hybridization involving s and p orbital. Now we are discussing about the sp3d hybridization, in which d orbital is also involved in the hybridization. So you can see here 1s, 3p and 1d orbital, right? In total 5 sp3d hybrid orbitals are forming. So here while drawing this structure, the point to be noted that these 3 orbital, right? These 3 sp3d orbitals should be in the same plane. Then these are the 2 orbital. These are the 2 hybridized orbital which is above and below the plane, right? Above and below the plane. I know that my drawing is not perfect. Whenever you are drawing the structure, it must be noted that these three orbitals should be in the same plane, planar, and other two will be the above and below the plane, right? Now, then let us take the example here. Then what will be the shape here, structure? sp3d means trigonal bipyramidal, right? Trigonal bipyramidal. Okay, here is the example, that is PCl5. First you have to calculate the steric number here. Steric number is equal to the number of sigma bonds, right? In the case of phosphorus, 5 valence electrons are present, right? In which 5 chlorine atoms are surrounding, which means that 5 sigma bonds for 0 lone pair, right? So steric number will be 5, which means that hybridization is sp3d hybridization. sp3d hybridization. Now, ground state electronic configuration of phosphorus, right? Ground state electronic configuration of phosphorus, that is equal to 1s2. Or otherwise you can write the electronic configuration of valence shell only. It is 3s2 3p5, right? Three is to 3p5. Then what will happen? We have to undergo the sp3d hybridization, right? So vacant d orbital should be here. One of the electron will go to here, so it will form the excited state of phosphorus. This is phosphorus, right? Phosphorus means it is 15, that is 3s2 3p3. It was my mistake, 3s2 3p3. Then what will happen here? One of the electron from the 3s will go to the 3d. Then it will form the 5sp3d2 hybridization. sp3d hybridization, right? sp3d hybridized orbitals are forming. So in total, overlapping of sp3d, right? sp3d, which means that chlorine is having 3p1 electron, right? 3p1 electron. 3p1 electron is the valence shell electron in the case of chlorine. So it will undergo the overlapping here. These electrons are coming from the chlorine. 5 chlorine is present, right? So finally structure will be this will be the sp3d hybridized orbital. Then it will undergo overlapping with the p orbital, right? P orbital of the 5 chlorine atoms. So it will form sp3d p sigma bond, right? 5 sp3d p sigma bond. Finally, you will get the structure like this. These three are in the same plane and these are in the above and below the plane, right? So we can represent these are the axial bonds. These two chlorine are in the axial bond and these three are in the equatorial bond, which means that axial bond having the bond angle of 90, axial and equatorial bond have the bond angle of 90 degree and this will be 120 degree. Clear? This will be the structure of PCl5. And the shape is known as trigonal bipyramidal. Clear? The last type of hybridization is the sp3d2 hybridization. Again, intermixing of one s orbital, 3 p orbital and 2 d orbitals. Then the structure will be these 4 orbitals will be in the same plane. Then other two will be the above and below the plane, right? These are the above and below the plane. This will be the hybridization of sp3d2 hybridization. Okay, here is the example, that is the SF6 molecule. So we can say that here in the case of SF6 molecule, first one you have to calculate the steric number, right? Steric number will be 6, which is equal to sp3d2 hybridization. Then find out the ground state electronic configuration of sulfur here. Sulfur it is 16, right? I am writing the excited state electronic configuration here. So you will get that 6 chlorine atom will forming overlapping here. This red represents the electrons coming from the fluorine here. So it will form sp3d2p, right? sp3d2p overlapping or p sigma bond. So in total the structure will be having 6 sp3d2p bond forming the 6 sigma bonds, right? Which means that these 4 are in the same plane having the bond angle of 90 degree. Again these two are in the above and below the plane having the bond angle of again 90 degree, right? This structure, this shape is known as the octahedral shape. Clear? Okay, we have few more points to discuss. I think we can discuss in the next class. I mean tomorrow. You have already maths class starting now by 6. Pratnya ma'am is waiting here. Now, okay, so far we discussed about the hybridization, right? Starting from the sp hybridization, sp2, sp3, sp3d and sp3d2 hybridization. Next class we will discussing about the sp3d3 hybridization and there are some problems also. So, I hope it was understood for everyone. Anyway, thank you so much all of you. Then, the reminder about the AITS, that is the All India Test Series for the JEE Main Session 2 and JEE Advanced. So just enroll this for it. Anyway, thank you so much all of you. Bye bye.